So we're recording. Any questions so far?
I
All
just had a
right.
quick I just had a quick one
Yes.
on the homework on exercise 5.4.
Let,
Um
let me look it up. Okay. What's about it?
um I was working with it and I was trying to figure out which theorem to apply, and I couldn't find any of the theorems in chapter 5 that seem to apply to it. Do we have to actually solve that matrix and then
No,
determine?
no.
Okay.
You need to use. I'm looking. Just stay with me.
Okay.
So is it stable? Um, so you need to use. I would say theorem 5.31. You need to write. You need to write it as ax plus bx. Take a look on example 5.31 and the following example how we did it on theorem 5.31. Okay, then that should do it.
Though I did do that, and I got that the norm of the BT goes to infinity from 0 to infinity, and it's not bounded.
um,
I might have something wrong, but
well, t e to the minus t is bounded. No, you need to do the integral.
yeah, the integral of the norm.
Yeah.
Um, the
how
norm is the
how
bottom
can it
row,
be?
and the integral of the bottom row, which is greater than the top row. If you do the
Okay,
there,
so
I'm
square root of e to the minus 1/2. Yeah, I see the 1 plus t to the minus 1/2 is a trouble. Oh,
Dr. Fool, James and I were talking about this on the side a couple days ago. I'm having the same problem. Like
okay,
I don't see how you.
I think there is a sign mistake. Thank you. The entry 1 plus t to the minus 1/2 is a troublemaker. I can see it. Is that what happened?
that's
I mean, I
correct.
think
Yes.
Yeah, because that goes to infinity if you integrate it. All right. Thank you very much. So,
the other issue is that I'm sorry, hang on. Zero solution is uniformly stable. Never mind.
no, as soon as that entry is fixed, it should be okay.
So what should we make it?
Um, 1 plus t to the minus 1/2. Just take it to the power minus 3/2. Make that entry to the power minus 3/2, and it should work. Darn it. I know. All right. Any other questions?
No more
All
for
right.
me.
Okay. Well, we were talking about Lyapunov function. So it is a V from 0 to infinity cross D into 0 to infinity. D is a subset of Rn. Should I change the ink to darker, or can you still read it?
It's good enough.
All right. So this is a positive definite. And we were talking about x prime equal f of x, right? And f of 0 equals 0. Positive definite mean v0 equals 0, v of x is bigger than 0, or x not 0. Okay? It's Lyapunov function if it is positive definite and v prime less or equal to 0, correct? Strict Lyapunov function if it is positive definite and v prime is less than 0. Okay? So this is basically, we're trying to summarize what we did last time. All right? So, um, so anyway, so in most of our work, the Lyapunov function v is of polynomial type of the form vxy equal to ax squared plus bxy plus cy squared. Okay? So now we're gonna, so you have seen already how we write Lyapunov functions. So this is bring us to theorem 7.11. So v, so I'm talking about this v here, is positive definite if and only if a positive and 4ac minus b squared is positive. Negative definite if and only if a is less than 0 and 4ac minus b squared is positive. Again. Okay? All right. So these are things that help us out. So let's take a look at an example. Let's take a look at example 7.1. So we're going to look at x prime equal minus xy squared, y prime equal minus y x squared. 0, 0 is a critical point. Okay? So you factor y here, and then you factor x here. But 0, 0 is a critical point. There are other critical points, but all I care now about 0, 0. So let vxy equal ax squared plus bxy plus y squared. So we want to choose A, B, and C properly so that V is a positive definite, and hopefully V prime is less or equal to 0. Okay? So go ahead and calculate V prime. So go ahead and do it. So it's clear that V0, 0 is 0. So we need to show Vxy is positive for xy different from 0, 0. We want so by properly choosing A, B, and C. Okay? So V prime is 2ax x prime plus bx prime y plus bxy prime. Oh, this is a C. There is a C here. cy squared plus 2cyy prime. So this is 2ax x prime minus xy squared plus b times minus xy squared y plus bx times minus y x squared plus 2cy minus y x squared. Okay? All right, so this is our V. So let us choose so let B equals 0, A and C be any positive numbers. Okay? Remember what the theorem says. Oh, we erased it. Oh, here. 4ac minus b squared is positive. So if I take v to be positive definite, if and only if a is positive, and 4ac minus b squared is positive, if I take b equals 0, then 4 times a times c is positive, and a is already by choice positive, a and c. So that's why be any positive numbers. Then by theorem, gosh, this guy keep calling. So v prime is, so b is 0, this is 0. Ya Allah. V prime is Oh boy. Oh boy. So we're going to have this one is v prime is minus 2a of x squared plus x squared y squared plus minus 2c y squared plus y squared x squared. So that is negative. Negative for x, y different from 0, 0. Okay? So this is what we really want. So based on the previous theorem, we choose A, B, and C so that first V is a positive definite, and then that told us, give us more information that V prime is less than 0. So we were gonna see that 0, 0 is asymptotically stable. We're gonna prove a theorem either today or tomorrow. Okay? All right. Any questions? All right. So now we're going to look at definition. Any question about this one? Look, if you do linearization, you should get the same answer. If you do linearization, you get xy equal to minus 1, 0, 0, minus 1, xy, a plus minus xy squared minus yx squared. Okay? Then if I look at, you see lambda equal to minus 1 minus 1. So by linearization, the zero solution is by linearization, is asymptotically stable. By linearization. Okay? So there we go. So you can do it both ways, but layup on a function is more general, give you better result in most cases. Any questions? All right. Now, let's take a look at, let's go back to 7.11. X prime equal f of tx, xt naught equal x naught, t bigger or equal to t naught, 7.1.1. And we know that f of t0 equals 0. That means the origin is an equilibrium point for the system. Okay? All right. So we're going to do some definition. And this is definition 7.16. These are before. The zero solution, or x equals 0, of 7.1.1 is a stable if for any epsilon positive, there is a delta that depends on T naught, X naught, so that if X naught less than delta implies XT, T naught, X naught is less than epsilon. Okay? Is B uniformly stable if delta is independent of the initial time. Okay? And C, it is asymptotically stable A dot S if it is stable and the limit as t goes to infinity of xt, t naught, x naught equals 0. Okay? So the uniform asymptotic stability in the book, I don't want to restate it because for Lyapunov functionals, we're not going to deal with uniform asymptotic stability. That will be beyond this course. Okay?
So for uniform stability, delta will still depend on X naught.
Yes, but not T naught. Okay? Because in the solution, you're going to have T naught. X naught. For example, let's take x prime equal to minus ax. A is positive, and x of T naught equal x naught for T bigger or equal to T naught. So the solution is x of T naught, x naught equal to x naught e to the minus a t minus T naught. That's what the solution looks like. Okay? And this is for all T bigger or equal to T naught or T minus T naught bigger or equal to 0. So let delta equal to epsilon, then if x naught less than delta implies xt, T naught, x naught is less or equal to x naught e to the minus a t minus T naught. This is less or equal to 1. This is less or equal to T naught, which is, right, less than delta, which is epsilon. So you see delta depend on x naught, okay? All right? So it is uniformly stable. Toward the end, there is no T naught toward the end. Okay? Any questions? All right. So now we're going to prove a theorem. And I'm going to do this proof only. Maybe this is the last proof I do for the course for you. And we're going to introduce a different notation like an open ball. Some of you had topology or real analysis, so you know what I'm talking about. If not, That's okay. I'm gonna describe it carefully. All right. Any question about this stuff? All right. Any questions? Okay. So we're gonna use a different notation now. Definition 7.17. Let X star be in Rn. It does not mean it's an equilibrium solution. And R is positive. Then B or X star denote the open ball, centered at X naught with radius R. All right, that is B of R of X star equal to the set of all point X in Rn such that X minus X star is less than R. Okay? So in other words, if this is X star, the center, and this is R, and any point has to be here. It cannot be here. This is not good. No. X has to be inside the circle because the distance from here to here is always less than R, or from here to here is always less than R. Correct? This is what it means. Okay? For example, if you have B21 or B01, so this means this point here, B01. So the point is, does 20 belong to B01? The answer is no. B20, this is 2 here. So the distance from here to here is bigger than R. And this is your R here. Okay? So this is not. So any point, for example, one half.
Would it be B10, not B01?
Let's see. Or yes. Thank you. Okay. So it's like a point inside the ball. All right. So let's define stability based on that. Okay. So let's rewrite the definition of stability. Okay? This is definition. Seven point 1.8. In equilibrium, point x star of 7.1 okay, is a stable if for every epsilon positive, there exists delta positive such that x0 less than BC x naught B delta implies x t naught x naught belong to B epsilon of x star for t bigger or equal to 0. So in other words, for any epsilon positive, so let's assume x star is the origin. So for any x star here, for any epsilon positive, there is a delta positive such that instead of then the solution starting here will be and this is epsilon. So delta could be less than epsilon. So this is the solution x. So x, this is xt, t naught, x naught will stay. So for any solution starting in the circle of radius delta, then the solution will always be less than another circle, less than epsilon. And of course, delta is going to depend on epsilon. So this is what it means. Okay? Okay? So I'm going to do the B is asymptotically stable if it is stable, if it is stable, and there exists a C positive such that x naught belong to B C of x naught implies xt x naught go to x star as t goes to infinity. Remember, x star is our equilibrium. If our equilibrium point was the origin 0, then this will be goes to 0 as t goes to infinity. So these are the definition of open ball, and it's helpful to do a proof for Lyapunov functions. So I am going to do a theorem here in a second. Prove a theorem. Any questions?
I assume this definition of stability is equivalent to the ones that we
Yeah,
did earlier.
yeah, they're totally equivalent.
Okay.
Yeah, because in any region, you can find an open ball. In higher dimensional, you can always find an open ball. Okay. I mean, we're looking at a scalar, but if you look at a higher dimensional, this is what the norm mean in higher dimensionals, right? Correct?
Yes.
So you see what I mean?
Mm-hmm.
Yeah. For example, if you take in dimensional x and y, what is the norm of x? If you take the norm of x to be the Euclidean norm, which is the square root of x squared plus y squared, square root of x squared plus y squared less than delta or epsilon, square both sides, you get a circle. X squared plus y squared less than epsilon squared, which is a circle, right?
Mm-hmm.
Yeah, so they're equivalent. But I wanted to introduce this notation because the proof of the next theorem depend on this kind of notation. I don't wanna throw you off, okay? But let me do an example first before I do the theorem on how to use this example here. How to use this definition. All right. So here is an example, and that is example 7.2. So let's take a look at x prime equal minus x, y prime equal minus 1. So 0, 0 is an equilibrium solution. Okay? So let x0 equal C1, y0 equals C2. Then the solutions are, the solution is x of t equals C1 e to the minus t, yt equals C2 e to the minus t, right? Now, for epsilon positive, let delta equal to epsilon. Then, for all C equals C1, C2 belong to B delta of 0. And what is that? B delta of 0, that is xy in R2 such that x squared plus y squared is less than C. This is what it means. Okay? Oh, B delta of 0, sorry, less than delta. Okay? This is delta. So we have xtyt less or equal to x squared of t plus y squared of t, that is equal to c1 squared plus c2 squared e to the minus 2t. This is equal c1 squared plus c2 squared e to the minus t. This is less or equal c1 squared plus c2 squared But what is C1 squared plus C2 squared? By here, this is less than delta because C is in this circle. Less than delta, but what is delta? Delta equal epsilon. There we go. And so, which implies xt, yt belong to b epsilon of 0. And that's it. So this is stable. Moreover, xt, yt is c1 e to the minus t, c2 e to the minus t, which goes to 0, 0, as t goes to infinity. So actually, 0, 0 is asymptotically stable. Do you see the how to apply the definition now? Okay?
Makes sense.
Makes sense, right? All right, we are ready now to prove our big theorem. Bear with me. Enjoy it. Lay back and enjoy it. And you will never be asked to reproduce something like that, but you need to see it. So can anybody tell me legally when is our final exam? Can somebody look it up? When is it? I looked at the calendar. I couldn't tell what day it is.
It's UD stated that it's the 26th if you look on their academic calendar, and if you go on the student schedule thing, that's what it says. It says the final date. The class starts this date, final date this date, and it's the 26th is what it says.
Or the 26th, that would be Friday?
Yes.
All right. So plan on your final being on a Friday. So we need to get things done because I need to travel too. Plus, I need to work on my tooth, extract one of my teeth and work on implant. I'll start on the 25th, the day before your final. We'll work it out like last time, but I don't want to drag it on three different days. The maximum is 2 different days, okay? So email me. I can do it Friday or Saturday. So email me. I'm going to send an email out and you reply to the same email, whether you want to do it on a Friday or Saturday. And again, the timing, would you prefer to work in the evening? If it was Friday, will you prefer it in the evening? Like, say, 5 o'clock. I don't want to say like 5 o'clock to like midnight or 10 o'clock. It shouldn't take you that long. Okay, and Saturday I can open it in the morning, 10 till like 7 or whatever. I'll give you the same amount of hours. Okay, think about it and let me know. All right. So we're gonna do theorem 7.12. Okay. Basically, if V is a Lyapunov function, for 7.1, then the zero solution is stable. So basically what I mean is V0 equals 0, Vx is positive for x not 0, and V prime less or equal to 0. This is what it means. Or you can read the theorem in the book. I stated it out. Okay? The layup on a function means this. V0 equals 0, Vx positive, and V prime is less or equal to 0. This is what a layup on a function means. Okay. Any question?
Is the layup on a function unique?
You wish.
Okay.
That's why there is a lot of research, right? Remember in the previous example, when we chose A to be positive and B equals 0, right? How many ways can you take A positive? For every value of A, you have a different layup on a function, right? Okay, so the answer is no. But your result about stability is as good as your layup on a function. You understand? If you cannot find the layup on a function, does not mean the system is not stable. Okay? You just need to work harder. Okay. So proof. We're going to pick an epsilon positive so that the sphere B epsilon 0 is in D. Now, what is D? Remember, V is from 0 to infinity cross D into 0 infinity. D is a subset of Rn, and 0 is in D. Okay? So I'm going to come here for now. I'm going to be flipping the board on you. All right. So let's take a look as a two-dimensional thing. So, all right. So this is our origin 0. And this is our D. This is our set D. And this is B epsilon F0. Okay? So we're gonna let S epsilon be the boundary of B epsilon at 0, because remember, this is an open. So I'm gonna take S to be the boundary of that. So that is S. Okay? All right. So since V is continuous and V0 equals 0, there is an M positive so that M equal to the minimum of X on SW of V. Okay? So if X is in here anywhere, then V has a minimum. Now, let B delta 0 be another sphere in D, okay? All right? So now V0 equals 0. So V is continuous. So we can choose delta positive so that Vx less than M for all X belong to B delta of 0. So I can take here, this is M, this is X. Let's say M is somewhere here. V of X less or equal to M. All right. So our goal is to show if X0 belong to B delta of 0, then X of T 0 X0, okay, belong to for all T bigger or equal to 0, bigger than 0. All right. So we're gonna show this is X naught. And remember, from here to here is delta, and from here to here is epsilon. Okay? Now, since V prime is less or equal to 0, okay, then Vx0 is less than M, implies that V of X of T 0 X naught is less than M, because it's decreasing. Okay? This is, since V is non-increasing long solution. Okay? So this in turn, implies that X0 cannot cross S of epsilon since V of x is bigger or equal to m, because m is the minimum. So that means, in turn, x t naught cannot cross S, cannot go above this. So if you have an x, that was gonna be always less than epsilon. Okay? Less than delta, but delta is less than epsilon, or you choose delta. So this implies the origin is stable. Okay? So this is really the stability of the problem. All right? So this brings us back here. If you can find a V where V is a Lyapunov function, then your equilibrium point is stable. So you have to have V0 equals 0, Vx is positive, and V prime less or equal to 0. Okay?
Quick question on your proof, Dr. Full. You essentially set V is equal to M because you said V is less than M, and at the bottom you said V is greater than M. V of X is greater than M.
Right, because since V prime less or equal to 0, then V of x naught is less than M. That means this is less than M since V is decreasing. Okay? So this is the contradiction here. And then, so since V is not increasing along solution, this in turn implies since V of x bigger or equal to M, this from here. Okay? Because M is the minimum, so that means V in total is bigger or equal to M. So it cannot cross. So this I am implying this is less than M to get myself ready for the proof for the final kill. Okay? So what you really need to do is find your V, find everything else that along the solution V prime is less or equal to 0, and you will get it. Let me do, before I run out of time, do an example. Let's see which example I wanted to do first. Oh, let's take this example. Example 7.3. So we have x prime equal minus y plus xy. Y prime is x minus x squared. So how many equilibrium points do we have? We have y prime equals 0, mean x equals 0 and 1. And we have minus y plus xy equals 0, y of minus 1 plus x equals 0. So this gives us y equals 0 and x equals 1 again. Okay? So the critical point is if I take x equal to 1, y could be anything. If I take x equal to 1, y minus y is anything. So in other words, I have 0, 0 as my critical point is one of them. And this is what I want for now. Now, Let's try linearization. So x prime is 0 minus 1, 1, 0, xy plus xy minus x squared. So a minus lambda I is lambda squared plus 1 equals 0. So lambda equal plus minus I. So 0, 0 is the center. And then the theorem on linearization is not applicable. So we cannot do anything. So we're going to use Lyapunov function. Okay? So let us try a Lyapunov function of the form So let us try v of xy equal ax squared plus by squared. AB are constant and positive. So we can easily see v0, 0 is 0 and vxy is positive for xy not 0, 0. Okay? All right, so what is v prime? 2ax prime plus 2by prime, 2ax x prime minus y plus xy plus 2b y prime x minus x squared. That is minus 2ax y plus 2ax squared y plus 2b xy minus 2b y x squared. How about if I take A equal B? If A equal B, these two will cancel out, and these two will cancel out. So I'll take anything A equal B. And in particular, A equal B equal 1/2. So your V is x squared over 2 plus y squared over 2. So this is 0. So V prime equals 0. So 0, 0 is stable. You see? So the derivative of V will always be 0. Okay? Now I want to go back to the previous example we did before. Can I switch the board? Right. All right. So let's take a look at the other example. Oh, you asked me about this here before. You know, this is Vx0 less than M, not Vx. Okay? This, because F is decreasing. So if you start and then here, so all it says is V of X is less or equal to M. But then any solution, any other solution, X not in this neighborhood will have to cross. So that means Vx bigger or equal to M. For any other solution cannot cross this S because since V is bigger or equal to M. So this is what it means. You have one inside and one in other solution. Okay, so let's go back to example 7.1. X prime is minus x xy squared. Y prime is minus y x squared. So if you look at the x prime equals 0, you get x minus x. 1 plus y squared equals 0, so you get x equals 0. You get y prime equals 0, mean minus y. 1 plus x squared equals 0, and you get y equals 0. So 0, 0 is the only solution here. Okay? And we chose V prime So we chose V prime to be equal to, I recall, what was it? Was minus 2 of 2a of x squared plus x squared y squared plus 2c of y squared plus x squared y squared. And you will see this is not 0. Okay? This is not 0. So this is going to be less than 0 if a and c are positive. So it's not less or equal to 0. So here, stability is going to be stronger. All right? It seems like stability is going to be asymptotically stable for this point here. Okay? And we will do a theorem next time that says if V prime is strictly less than 0, then you will get better stability. Actually, you will get asymptotic stability. Okay? Any questions? I think I'm going to stop here for today, and we will pick it up from here. So I'm going to do the asymptotic stability. So assume I did theorem 7.1. Okay, I need you to look at 7.13. So if V is strict, the Lyapunov function for 7.1.1, then x equals 0 is asymptotically stable. That means v of 0 is 0, v of x is positive for x not 0, and v prime of x is strictly less than 0. Then you will get asymptotic stability. And I'll pick it up from here next time. We will show instability too, and then we should be done. Okay? All right. Any questions?
Chris had one in the chat.
Yeah. You said what?
Chris has one in the chat.
Oh, there's a question in the chat. Okay. Are there a finite number of Lyapunov functions for a given system, or at the very least, a finite number of families? You know, there are infinitely many, but for a different value, I don't know. Does every problem have the same thing? I don't know. Also, is there any kind of linear independence, superposition principle kind of things lay up? No, it doesn't really matter. I mean, look, you see, for the previous, Lily, stop it, it's daddy. Lily, it's daddy. You can take, for the previous example, you can take x squared plus y squared, or you can take vxy equal 1/2 x squared plus y squared. Not for this example, for this example, and they will both work. Okay? It will both give you v prime equals 0. It doesn't really matter. All right? So, again, it's can I take, for example, v equal to x plus y? Let's say I do that. Then v prime is x over x, x prime, plus y over y, y prime. So that is x over absolute value of x. X prime is minus xy squared plus y over y, y prime minus y x squared. So let's see what this gives us. So this is equal to minus x squared minus x squared y squared over x plus minus y squared minus y squared x squared over y. So this is minus of x squared plus y squared over x. Sorry. This is minus x squared of 1 plus y squared minus y squared over y times 1 plus x squared. Now simplify. This is minus x times 1 plus y squared minus y times 1 plus x squared. Okay? Well, hell, this is less than 0. For xy different from 0, 0. Guess what? This is a better Lyapunov function than the other one, and this gives us actually the other one. Yeah, we just did this one a little bit ago. It gave us 0, didn't it? Yeah, it gave us 0 if I take A equal B. Actually, with this Lyapunov function, 0, 0 is asymptotically stable, it seems like. So this is even better result. You see, there is not one unique Lyapunov function. As I said at the beginning of the lecture, the stability is as good as your Lyapunov function is. And I did not discuss with you how you take the derivative of the absolute value, but this is what it is. How do you take the derivative of the absolute value? Equal to the square root of x squared, that is x squared to the 1/2 d of dt. And this is 1/2 x squared to the power minus 1/2 times 2x x prime times the derivative of the inside. So if I work on this 2, 2, so I have x prime over x squared and let's see. No, over the square root of x squared, right? And then that is x over absolute value of x prime. You see, very clever way to do to differentiate the absolute value of x with respect to time. So that's what you will get, x over absolute value of x. So actually, this Lyapunov function. Thank you for your question. If I do revision of my book, I will include this in my book, a new edition. Actually, this gives you a better result, okay? Based on Lyapunov functions. All right, any questions?
I had a follow-up from the question at the start of class.
Yes, what is it?
So James had asked about the 5.4.
Yeah.
And this is what I was trying to think of earlier. The eigenvalues for that, I was trying to ask someone, no one responded. So I think I'm right here, but the eigenvalues are -5 and 0. And so theorem 531 wouldn't even apply because it's not uniformly stable then.
Okay. Then you need to look at the fundamental matrix, if that is the case, okay? You know what I mean?
Mm-hmm.
Yeah.
I think an earlier theorem applies because where is it?
They do.
5.14 would.
Okay.
Because that says non-positive real part.
Okay. All right.
It mentions stability.
Yeah.
But it's not uniformly stable is the issue.
The problem asks for stability, not uniform stability.
Yeah, I don't think the problem asks for uniform stability. All right, I'll look into it. Thank you. Any other questions? So we're getting into the interesting stuff. This stability stuff is very interesting. So what do you think of this course? Learning something? Well, I hope you are. It's very fast, but this is the best I can do for you. Okay? And I'm really following my book because I wrote it, and this is how I rearranged my notes when I taught it in the past. And I believe this is a good layout. So, all right, the material follow nicely. Any questions? All right, I'm gonna stop recording. And I'm gonna